So the last thing we look at when we're talking about valence bond theory is looking at what happens in molecules when we have multiple bonds, so double or triple bonds. And so what we typically look at for the overlaps we've been talking about, we call those sigma bonds. So we have SS overlap, SP, S hybrid, P to P end, and hybrid overlap. So different ways of orbitals overlapping. So looking at the sp3 hybrid orbital of carbon overlapping with the s orbital of hydrogen, that was an sp3s, so an s hybrid orbital overlap, forming that sigma bond. Okay. But we need to deal with what happens when we have double bonds. How do we explain the overlap happening there to predict those bonds? So when we have a multiple bond, when we have a double or triple bond, what's really involved is that the double bond contains a sigma bond, so the same things we saw in our single bonds, but it also contains a second type of bond, which is called a pi bond. And we can't actually form pi bonds when we have sp3 hybridization. We can only form them when we have sp2 or sp hybridization because it requires that empty p orbital. Remember when we formed the sp3 hybrid orbitals, what we saw is that all of the p orbitals were involved in the hybridization, so there are not any empty ones available to form these pi bonds. So if we have double bonds, okay, we can have those when we have sp2 hybridization. We can have sp hybridization, we can have triple bonds, and we actually get one sigma bond, which is the same thing we saw previously, and two of our pi bonds. So a double bond is a sigma bond and one pi bond. A single bond is just a sigma bond. So we're going to look at a double bond here, but we're going to look at it in parts. So first we're going to look at it in terms of the sigma bond. And so this is what's happening in our sigma bond. We have the sp2 hybrid orbital of carbon. So this is an sp2 hybrid orbital overlapping with an sp2 hybrid orbital. And that forms that sigma bond, that framework for that. The second part of the double bond is the pi bond, and it's formed from this side-to-side overlap. So we have that empty 2p orbital on the one carbon, the other 2p orbital on the other carbon, and we get this side-to-side overlap between those. So we kind of get this lobe above and below the bond, or on either side of the bond, and that's actually the pi bond. So both of these together are actually showing us the pi bond. We still have our sigma bond here, which I'll color in blue there. That's our sigma bond, so that and the pi bond together make a double bond. So there's two lobes in that pi bond. Now when we go to a triple bond, we see the same thing. We see our sigma bond framework, so we have our sp-sp hybrid orbital overlap to form the sigma bond. And then we go on to form the two pi bonds. And so what we have is a lobe on top and bottom, that's one overlapping p orbitals, and then we have a lobe in the front and in the back here, okay, that forms the other pi bond. And so we almost get like this cylinder around there because we get these lobes that kind of all start running into each other. And another way we can kind of show this, kind of zoom in a little bit, is we have overlap between this p orbital and this p orbital, as well as overlap between this p orbital and this p orbital. So together, even though it looks like they're making four lobes, two lobes makes up that pi bond. So when we look at this question, how many sigma and pi bonds are in aspartic acid, we want to look at our structure and look at how many sigma and pi bonds we have. So what we need to do is go through and count the bonds. So remember, a single bond is a sigma bond. So we're going to first count our single bonds. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have 12 single bonds. Notice that's not necessarily the same as sigma. So we have 12 single bonds. And double bonds, we have 1, 2 double bonds. Remember that each double bond equals 1 sigma plus 1 pi. So in reality, we have 14 sigma bonds and 2 pi bonds. And so A is going to be our correct answer.